Welcome back to the deep dive. Today, we are immersing ourselves in a fascinating challenge to the conventional wisdom of large language models.
hmm
For years, the reigning assumption has been that capability is just directly proportional to scale more parameters, more data, better results.
Right. Bigger is always better.
Exactly. But what happens when we look at complex, abstract reasoning tasks, specifically something like the ARC-AGI benchmark?
Well, you find an efficiency paradox. You have these small, universal, transformer-based models, and they're trained from scratch, mind you, without relying on that internet-scale pre-training.
And they're just winning.
They're consistently and dramatically outperforming standard, immense transformer-based LLMs on these pure reasoning tests.
Okay.
So this deep dive is all about unpacking that why, systematically analyzing the sources of these gains.
And our source paper really digs into the architecture of these universal transformers, or UTs. They challenge that prior idea that the success comes from, elaborate or specialized architectural fluff.
Exactly. Instead, they isolate the true power source.
Mm.
And it comes down to two things: a specific recurrent inductive bias and the strength of the model's internal nonlinear components.
So our mission today is to understand how these elements were optimized.
And what the resulting model actually achieved. That resulting model is the Universal Reasoning Model, or URM.
URM.
And it really pushes the boundary for this whole category of small, efficient models. I mean, URM achieves state-of-the-art performance with 53.8% pass at 1 accuracy on ARC-AGI-1.
Which is already impressive.
It is. And a highly competitive 16.0% pass at 1 on the notoriously difficult ARC-AGI-2. These figures aren't just incremental improvements. They represent a significant step change in efficient reasoning capability.
Okay, so before we jump into URM's enhancements, we really need to ground ourselves in that foundation. Let's start with the fundamental difference between a standard transformer and a universal transformer, because that distinction is everything here.
It's the whole game, exactly. When you look at a standard transformer of, say, 32 layers, you are dealing with a stack of 32 distinct layers.
Each with its own set of weights.
Each layer has its own unique set of parameters. So this design means your total computational cost and your parameter count, they scale linearly as you add more depth.
The very rigid coupling.
Very. If you want more capacity, you have to add more parameters and you increase your runtime. It's that simple.
But the universal transformer is, well, it feels much more elegant. It changes the depth dimension entirely.
It really does. Instead of stacking distinct layers, the UT introduces recurrence over depth. So it applies a single shared transition block, the same set of parameters repeatedly.
Or a loop.
In a loop, sometimes 10 or even 20 times. This weight tying across depth is the core mechanism.
So by reusing those attention and transition parameters for every single step,
You introduce a powerful recurrent inductive bias. Think of it less as a fixed network and more as a single algorithmic unit that's running these iterative refinement steps. It allows the model to process information sequentially over a much longer effective depth, but without the parameter count just ballooning.
And this iterative process is what the research identifies as the real source of its reasoning power. And of course, that's superior parameter efficiency.
Right. It suggests that complex reasoning on tasks like ARC-AGI fundamentally requires this kind of multi-step sequential deliberation, not just a massive fix-with network.
And there's data to back this up.
Oh, absolutely. The concrete evidence is in the comparative data. Let's consider a scenario where we pit a standard massive transformer against a small UT. A UT with just 4 base layers and 8 recurrent loops.
So pretty small parameter count.
A relatively low parameter count, yes. It achieves a 40.0% pass at 1 on ARC-AGI-1. Now compare that to a vanilla transformer that uses an astonishing 8 times the compute and 32 times the parameters.
32 distinct layers.
32 distinct layers, a 512-dimensional hidden size. That massive vanilla model only manages 23.75%.
That comparison is, well, it's the thesis statement of this entire paper. It just completely shatters the idea that brute force scaling is the only way forward for reasoning.
Really does.
The UT is proving that architecture matters profoundly. It's efficiently converting its computation budget, its FLOPs, into increased effective depth for this kind of multi-step algorithmic reasoning.
And the efficiency story is just so compelling. The recurrent computation essentially grants the model higher theoretical expressivity than a fixed depth transformer with the same number of parameters. And on top of that, it allows for adaptive computation time, or ACT.
Right, ACT. That's critical for optimization.
It is. It's the mechanism that lets the model decide how many recurrent steps or loops a particular token actually needs.
So simpler tokens can finish early.
Exactly. They might halt early, while complex tokens that require that deep multi-step reasoning can just keep iterating through the shared block. It allocates compute only where it's actually needed. This enhances both efficiency and reasoning fidelity.
Okay, so with that foundation in place, the authors of the URM paper basically asked, how do we strengthen the elements we know are working?
Recurrence and nonlinearity. And they developed two primary enhancements built upon a decoder-only UT design.
The first one focuses on nonlinearity. It's the Conf-Jiu block. I know ablation studies in the paper confirmed that the feed-forward network, the MLP, is the primary locus of nonlinearity, not the attention mechanism itself.
Which is a key insight. That's where they decided to focus their efforts. Their goal was to enhance the standard SWIGLU FFM block, which was already state-of-the-art in a lot of transformer models.
And Conf-Jiu augments this.
It does, by injecting explicit local interactions. They achieved this by adding a depth-wise short convolution right inside the gated representation projection.
So for our listeners, the standard SWIGLU is pointwise. It operates on each token's expanded representation independently. But this convolution, it changes that whole dynamic.
Completely. It explicitly injects lightweight channel mixing and local contextual interactions into that vital nonlinear pathway.
And this is where the paper gets really rigorous. You might just assume that adding a convolution anywhere would help, but that they tested a bunch of different insertion points.
And what was so fascinating was that the benefits only showed up when the short convolution was placed after the MLP expansion in that high-dimensional nonlinear subspace.
So not before.
Placing it earlier, maybe in the attention pathway, was often detrimental to performance.
Which suggests that the most critical moment for this kind of lightweight local mixing is when the features are maximally diverse and separated.
Precisely. It's not about mixing the raw inputs. It's about mixing the expanded, transformed representations right before they get projected back down.
And the impact was visible.
Oh, it was tangible. The paper shows that integrating Conf-Jiu led to more structured and diverse attention matrices. It's a clear sign that this enhanced nonlinearity was facilitating better interchannel information flow. And that's crucial for abstract reasoning where patterns rely on these intricate feature combinations. This one architectural change alone contributes so much to the performance leap.
Okay, so that handles the architectural capacity. But as you mentioned, recurrence, for all its efficiency, introduces a pretty severe training challenge. That brings us to the second innovation. Truncated backpropagation through loops, or TBPTL.
That's right. When you force a single block to run for a large number of recurrent loops, let's say 8, you essentially create an extremely deep network just in the depth dimension.
And propagating gradients all the way back through that is a nightmare.
It's prone to massive instability and noise accumulation. It can severely hinder optimization.
This sounds very familiar to anyone who's worked with standard RNNs and had to use truncated backpropagation through time, or TBPTT.
It's the same conceptual principle. You're just applying it to the depth dimension to stabilize that recurrent computation.
How does it work here?
Well, TBPTL mitigates this by partitioning the recurrent rollout. The first segment, loops 1 through n, is treated as a forward-only pass. No gradients. Then, the second segment, loops n plus 1 through m, that's the trainable part. Gradients are only computed on the loss accumulated in that latter, more stable window.
So you're only grading the most recent steps of the iterative process. It keeps the optimization trajectory stable. Did they find a sweet spot for that truncation point?
They did. Empirically, with 8 total inner loops, they found that truncating the first 2 loops, so leaving 6 loops for gradient computation, achieved the best performance.
That's a very specific balance.
It really highlights the critical balance they struck. You need enough recurrent steps to allow for that long horizon learning, but you absolutely have to truncate the early loops to prevent the noise from destabilizing the weight updates.
Okay, let's pull back and look at the cumulative effect of these two innovations, Conf-Jiu and TBPTL. Looking at the final URM performance against previous UT approaches, the lead is just undeniable.
Absolutely. Reviewing the main table, URM gets 53.8% pass at 1 on ARC-AGI1. That dramatically surpasses TRM's 40.0% and HRM's 34.4%.
But the gains are even starker on ARC-AGI2, the really hard one.
That's where it really shines. URM's 16.0% pass at 1 is nearly triple HRM's 5.4% and more than double TRM's 4.6%.
The scale of that improvement on ARC-AGI-2 is highly significant. It suggests URM's architecture isn't just slightly better, it's it's fundamentally more capable of representing that complexity needed for true abstract reasoning.
And furthermore, the study noted that URM's performance advantage widens considerably when they increase the sampling budget, say, looking at pass at 1000.
What does that imply?
It implies that the architectural changes support a much richer process of iterative refinement, and that translates directly into generating a larger pool of high-quality candidate solutions. The model is just exploring the solution space more effectively.
And to really hammer home why these nonlinear components are so necessary, we have to look at the ablation study. This is where they prove their hypothesis by just, systematically removing pieces.
And this ablation provides what I'd call incontrovertible proof. The full URM baseline starts strong at 53.75% pass at 1. If we remove just the short convolution, our conv/GLU enhancement performance immediately drops by over 8 percentage points to 45.25%.
Wow, just from that one change.
Just from that. Then, if we replace the advanced SWIDLU activation with a simpler, less expressive SWIDLU activation, the score just collapses to 29.75%.
And the most profound drop, which confirms the essential role of these nonlinear transformations.
When they remove the attention softmax. It's a necessary but weaker form of nonlinearity, and without it, performance virtually vanishes. It falls to 2.00%.
2%.
The clear step-by-step decrease across these tests validates the central finding of the entire research. The ability to perform complex abstract reasoning tasks like ARC-AGI hinges on having rich, expressive nonlinear mappings located primarily within the FFN. Weakening this nonlinearity just systematically limits the model's capacity for reasoning.
It's incredible that they optimized the architecture so successfully. But that's only half the problem, right? Once you have a theoretically capable model like URM, how do you actually train this beast efficiently? Especially with the complex, non-convex loss landscape from these deep recurrent structures.
Right, so the research turned its focus to the optimization process. They investigated training efficiency by comparing the standard Adamantane 2 baseline against a more sophisticated technique, the muon optimizer.
Momentum updated orthogonal Newton?
That's the one. Muon is specifically designed to handle these complex loss landscapes by dynamically approximating second-order curvature information.
So, given URM's deep shared weights, you would expect muon, with its ability to navigate the spectral properties of recurrent weight matrices, to offer a pretty big advantage over a first-order method like Adam.
It did, but only in a specific way. The data shows a substantial advantage in convergence speed. Muon demonstrated nearly a twofold speedup on ARC-AGI-2. It was hitting key accuracy milestones much earlier than Adamantane 2.
So it's more efficient.
It confirms its efficiency in navigating that initial challenging optimization space.
But, and this is where the results get really thought-provoking, the asymptotic performance.
They converge to the exact same final accuracies, 53.8% and 16.0%.
So a faster path to the same destination.
This is a textbook finding on the separation between optimization efficiency and architectural capacity. Muon successfully reduced the training cost. It accelerated convergence.
Validating its use for these complex dynamics.
Absolutely.
Yeah.
However, it did not manage to push the model past its final generalization ceiling.
Which implies that the ultimate capacity limit is fundamentally governed by the URM's architecture itself, the expressive power from the conv/LGLU and the recurrent bias, not by the limitations of the optimizer being used.
Exactly. The architecture defined the peak performance. Muon just shortened the time it took to get to that peak.
So let's summarize.
The fundamental realization here is that the recurrent inductive bias in the universal transformer is just superior for parameter-efficient, depth-intensive reasoning on these abstract tasks. It's better than brute force scaling. And URM successfully pushed this capability further by reinforcing the critical components, conv/GLU for that necessary local mixing in the FFN's nonlinearity, and TBPTL to ensure stable optimization.
So what does this all mean for the future design of reasoning systems? We now have this conclusive evidence that architectural efficiency is superior to raw scale for abstract reasoning. We also know that a sophisticated optimizer like muon can speed up training, but it can't overcome the final generalization ceilings set by the model's architecture. The provocative question this leaves you with is, are we hitting a fundamental representational limit defined by the current structure of that recurrent block? And if we are, what architectural or parameterization shifts are required in future recurrent models to genuinely leverage advanced second-order optimization for higher asymptotic generalization performance to push past that ceiling defined by Adamantane 2 convergence? That right there is the next great challenge.